am I capturing? Is it capturing or not? Bring that back up. Okay, definition of the derivative. This is important to you and me. So if I say find the definition of the derivative, I expect you to manipulate this formula. Okay, which is what we did in 2.4 and again in 3.1. I don't know if the AP exam will give you that formula. I might put it at the top of your page for your chapter test and say, if you don't know this by the end of the year, I don't like you. Okay? But that formula is important to me. There's other two definitions for derivatives at points. I don't tend to use them very much. I just use the top formula because it's consistent throughout. Right-hand derivative as h approaches 0, as h approaches negative 0, or 0 from the left. Yeah, whatever. It's the same version as the formula at the top. Do you look at it that way? I mean, I'm the guy that sees patterns easily. I see that this is the same as this, is the same as this, is the same as this. It's just being written in slightly different ways. The shape of the formula is the same no matter what. Okay? Okay. So some formulas. So if I walked into the room and I said, use the definition of the derivative to find the derivative of x squared, lo and behold, you would find out the answer is 2x. And then somebody says to you, Mr. App, would you do the same thing for x cubed? Yeah, I could ask you to do y equals x cubed on your chapter test for unit 2. And when you did that, you would get 3x squared, and you would be proud. And then x to the fourth, you would do that one using the definition of the derivative, and you would find out that it would be 4x cubed. Hey, Mr. App, I see a pattern. Anybody care to throw the pattern out? So if you had x to the 7th, its derivative would be 7x to the 7 minus 1, 6. Good. Okay. Mr. App, the next one's a line. All lines have m as their slope. Oh, so this one has a slope of 3. This one has a slope of m. The next one kind of trips you up a little bit, because if you're not paying attention, those next two are horizontal lines. What are the slopes of horizontal lines? 0. Because if you graph y equals 3, it looks like this. And we all know what the slope of that line is. Okay, next one. Ep's starting to make me think a little bit. So you've got some margin room somewhere? Yeah? Okay, margin room, here we go. So we're going to use the definition of the derivative to do these two. So f prime of x equals the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. This is good practice for Friday's test. I know I'm too loud. Mrs. Pelzer's just closing the door. Okay, so get a common denominator or multiply by a fancy form of 1. What do you want? Multiply by a fancy form of 1? Okay, so the grand common denominator is x times x plus h. Do you agree? What? Because you can't. You can, but it won't help. I'll show you why that's not right later. Okay. X plus h, x plus h, x. So I'm going to multiply that into my brackets. And when I do that, I get, okay, I'm going to skip a step. Unless, well, I'll try and skip the step. If you don't like what I'm doing, then say, please put that step in. So anyways, you go x plus h times x all over x plus h. What happens to the x plus h's when you multiply it into the first term? You just get x. The x plus h's cancel. And when you take the blue, the stuff in the gray circle, and you multiply it into the second term, x plus h times x divided by x, what happens? The x's cancel. You're left with x plus h. And your denominator doesn't change, Mr. Up. Just write it down. Okay. H, x plus h times x. How's that? Are we good? If you don't understand what I did from here to here, put a star and ask about it from me later. There's a line in the middle that I didn't put in that you could put in. Okay? So, what happens to the brackets when you drop them at the top? You get f prime of x equals limit h goes to 0 of negative h over h x plus h x. The h's cancel. You're left with okay, but maybe okay, I'm not going to skip this step, but I'm going to skip it in 10 seconds. I'll say you probably don't have to write this down, but it doesn't hurt. And then you get, and then you can put 0 in for h, and you get, and you can drop the limit statements here, so you get negative. This is a line that I probably wouldn't put in as well. I'm just going to go to there. And that would be skipping 0 steps. I guess I skipped 1 step. Let's zoom out. So the lines that I need to see from you are this one, this one, this one, and this one. Okay? You can have all of them there, but the ones that I put the check marks next to, I need to see. Okay? Yeah, you'd have 4 lines of work. It'd be out of 3. Yeah. The definition of derivative questions for me are always out of 3. I guess it could be out of 5 if it was nasty, but this, contrary to popular belief, this isn't nasty. This is motherhood and apple pie. Straightforward. Here comes the pitch. Swing at the fastball. Okay? Here it comes. Forget the curveball, Ricky. Throw in the heater. So you guys aren't sports fans. You wouldn't even know where that's from. What movie? No. Major League. Worst baseball film ever. So, the next one. Square root of x. So it's square root of x plus h minus the square root of x all over h. Okay. So, instead of getting rid of the instead of getting a square root off the denominator, here's actually where you want to get the square root on the denominator. You want to move the square root around. So the only method that we know of that allows kids to move square roots from bottoms to tops of fractions, really bad way of saying it, but allows you to move the root around, is to use conjugates. So we're going to multiply by a very fancy form of 1. And this is one of the questions on the practice test made you do this. So you're going to multiply top and bottom by root x plus h plus root x. Root x plus h plus root x. So you do that, and you think to yourself, why did I do that? Well, beautiful things happen. I know it's kind of hard to see, but root x plus h times root x plus h. X plus h, the square root is gone. Root x plus h times root x, and minus root x times root x plus h. 0. Minus root x times plus root x. Minus x. That's why we love conjugates. It gets rid of square roots where you don't want them. It moves them to the other place. You have to kind of live with them appearing down there, but at least they're out of the way. It's like kicking your brother out of the house. You've got to get him out of the way. Boo. No? Okay. Anyways. What happens to the numerator? The x's cancel. You're left with h over h root x plus h plus root x. And we think that's pretty cool because h's cancel. Okay, do we want this over 2 steps or all at once? Okay. So put 0 in for h now, and you're left with 1 over root x plus root x. Oh, that's 1 over 2 root x. How's that? Okay, be prepared to be amazed. Oh, just everybody put your seat belts on. Click. Ready? Ready? No, you're not. So the function that we started with first was y equals 1 over x. Mr. Epp, I don't like fractions. Oh. That's the same thing. Would you agree to that argument? And then I'm going to use the rule that Alana just said to us a couple of minutes ago. Its derivative, to find the derivative, all you do is drop the exponent down and take 1 away from it. And then you can use your exponent rules that you learned in grade 9 and write it as, and you're finished. Same thing with square roots. Y equals square root of x. Mr. F, I don't like square roots. I remember from math 10 and math 12, because Mr. F beat it into me, that the square root is in fact the 1/2 power. The derivative, drop the exponent down out front and take 1 away from positive 1/2. You get negative 1/2. Mr. F, I don't deal with exponents very well, so maybe I could do this and then do this. Is it not a beautiful thing? Riley's not sure. You're letting it wash over you right now. Yeah. Yeah. So from here to here, it's just the 1/2 power, and I'm just switching it back into square root. Does that kind of make sense what I'm doing there? Oh. Yeah, we got to start teaching kids calculus in grade 10. Yeah. You just use an exponent rules.
That's so much faster.
It is so much faster. Yeah, Luke. Or is it Cam that's asking the question? Yes. Yeah, then that's where the negative 1, yeah, that becomes there. Take 1 away from negative 1. Negative 2. So that it's just following the pattern. It's just following the pattern that we used here. X cubed's derivative is 3x squared. X to the 4th is 4x cubed. Drop the exponent down out front and take 1 away from the exponent. Drop the exponent down out. Hey, Mr. Rep, even works for this one. Drop the exponent down out front. Take 1 away from the exponent. Hey, anything to the power of 0 is 1. So that makes sense then. It's the same answer. Is this rule cool? Do you think this rule is powerful? Guess why it's called the power rule? Because it deals with powers. Unless I say use the definition of the derivative. I know everybody gets their nose scrunched up and goes, really? I have to do it the other way? Yes. Before you can run, you have to learn how to walk. Oh, this is, sure, it's crawling. Before you can run, you have to learn how to crawl. At least you can check your answers. Okay. At the bottom of the page, what does it say? It says, we also learned, whoa, crap, how a function might not have a derivative. So sometimes some derivative might fail to. The function will not have a derivative at a point where the limit, where the slopes of the secant lines don't approach the same number a. That's what it's saying here. So you're thinking to yourself, what is he getting at? Everybody graph y equals absolute value of x in their calculatrice, please. Derivative is slope. So if I ask you to... Well, no, or it has two different slopes. So if I ask you to graph y equals absolute value of x, it looks like this. Tell me about the slope on the left of 0. Negative 1. Tell me about the slope on the right-hand side of 0. Positive 1. We call x equals 0 a corner point. Because it causes what in the derivative graph? You betcha. Yeah, they're both open because we don't know quite what's going on at 0. Jump discontinuity. Whatever. What? Well, we can't say what's going on 0 because it switches. Goes from negative slope to instantly positive slope. Okay, graph y equals 2x to the 2/3 power. So in our calculator we would type it like this. And then when you do that, you can laugh at me, but basically it looks like this. Yeah, it looks like a flock of seagulls. Yeah. Where slopes of the secant lines approach infinity from one side and negative infinity from the other side. So what it's saying here is the slope is negative and getting more negative, and then on the other side it's positive and getting more positive as I fall into the black hole. It's a cusp. If you graph the derivative, it looks like this. What's on the derivative graph? Tell me where the vertical asymptote is. There you go. Vertical asymptote at x equals 0. So on the derivative graph, you'll have a vertical asymptote at x equals 0. On the original functions graph, you will have a cusp. Vertical tangent. Okay. Okay, so as I move, I'm going to use the eraser. So small negative slope, getting bigger, getting bigger, getting bigger, better and bigger, bigger, more and more negative, more and more negative. If I zoom in, it's almost like you're falling into a black hole as you get to zero. If you zoom in really close to zero, you'll see that V shape getting steeper and steeper and steeper. Yeah. And then as you fall in this way, it's small positive, you can get bigger positive slope. Holy wow, it's big positive slope. Oh my God. Anyways, so that as you get really close to x equals 0, your y values, the slopes on either side of the 0 are positive infinity and negative infinity. The slopes. Okay. You get it? You see it? Okay. Yes, here? Nothing? Okay. So cusps. Cusps are bad. So we've got corners, they're bad. Cusps are bad. Vertical tangent. Anybody graph that on their calculator? Chemistry people? What's that point called at x equals 0? I'm going to be offended if nobody knows. I'm going to tell Mr. Pelzer, and you will all fail Chem 12. Equivalence point. In math, we call it a vertical tangent because you are climbing fast. Yes? Going vertical, dude. Okay, if I graph the derivative of that, or if I graph the slopes are small, positive, oh my God, large and positive, and then, anyways. Small positive, OMG, large positive getting smaller and positive. When you graph it, look the kind of discontinuity it creates. But a different kind of infinite discontinuity. Infinite discontinuity. Okay, number 4. A discontinuity, which will cause the one-sided derivatives to be non-existent. Okay. Doesn't really even matter. X equals 0 is bad. End of sentence. Okay? So there are 4 things you're going to look for for you to find the derivative. We have to be continuous, and then it can't be a corner, it can't be a cusp, and it can't be a vertical tangent. If we're finding the derivative at any of those points where it's not continuous, or it's a vertical tangent, or it's a corner or a cusp, the answer is, I can't do it, go find somebody else. And they'll say the same thing. I can't do it, go find somebody else. So as long as you're not in any of those 4 spots, you can find the derivative.
So on that graph, the graph, you just find the derivative at x equals 0.
Right. You can find anywhere else, but 0 is bad. Actually, 0 is bad for all 4 of these examples. And they're all different kinds of discontinuities. I could have an infinite like this could be just y equals f of x, right? We can't find the slope at x equals 0 because the function's discontinuous there, right? You get what I'm saying? 4 things, 4 bad things. Okay, so find the points in the domain where is not differentiable. Okay, graph it in your calculator, please. Tell me where the problem is. Corner point at x equals to, very much like a biology person right now. We just classified problem. Ouch. Sorry, biology people. Bit of a shot. No? No. Is that it? That's it. Okay. I did want to show you one other thing on your calculator. So this is for all those little kids out there in La La Land. Your calculator will do calculus for you. So if I had the function x squared, and I wanted to find the slope at x equals 3, Mr. App, please find the slope at x equals 3. Trace, second trace, derivative, x equals 3. Mr. App, the slope is 6. Sure, I don't care, but it's not going to help you because I'm going to say use the definition of the derivative too. And if I don't, you can always check your answers. If I don't see the definition of the derivative, I don't mark the question. Second trace, derivative, dy over dx. Sweet, huh? Now if you buy the super fantastic TI Inspire CAS, it will actually do, it won't do the definition of the derivative, but it will do algebraic derivatives. This isn't algebraic. All of this previous page is, it can do all of this. It just can't do the work on the left and the right for you. But it can do all those derivatives. You just type it in, say derivative, and you type in the function, you close brackets, you hit enter, it spits out the answer. Wolfram Alpha does. Do I use it? I don't know. What do I need it for?
You're calculating yourself.
Oh, thanks. TI-80 app. TI app Inspire. There we go. Okay. There you go.